All right, we're going to get started. Good afternoon, everyone. Thank you for joining us today for our weekly robotics colloquium. Today we have Zsolt Kira, and he will be presenting his talk titled Towards Long Horizon Robotic Task Learning. Zsolt Kira is an assistant professor at the Georgia Institute of Technology and the associate director of Georgia Tech's Machine Learning Center. His work lies at the intersection of machine learning and artificial intelligence for perception and robotics. His current projects and interests relate to embodied AI, focusing on tackling more complex compositional tasks and the integration of learning and planning. On the machine learning front, his group has made significant contribution to moving beyond current limitations of supervised machine learning to tackle unsupervised, self-supervised, and semi-supervised methods out of distribution detection and model calibration, learning under imbalance, continual lifelong learning, and adaptation. He is especially interested in the intersection of these in order to fully leverage the stream of data that embodied robotics typically encounter. Professor Kira has grown a portfolio of projects funded by NSF, ONR, DARPA, industry, and the IC community. He has over 45 publications in top venues and has received several Best Paper Student Paper Awards. You are more than welcome to ask questions during his talk via the chat, and I will read them out, or feel free to leave all of your questions until the end of the presentation. So, Dr. Kira, welcome. I know we're all excited to hear your presentation today, so please take it away.
Awesome. Thank you for the opportunity and the introduction. So today I will talk about towards long horizon robot task learning. And again, I'm at Georgia Tech, affiliated with the Robotics Institute, as well as the Machine Learning Center that we have there. So here's an outline of my talk. I'll start by just briefly motivating the problems that we're interested in, and specifically highlighting key areas that I think are crucial in solving these problems. I'll talk specifically about the importance of simulation and benchmarking for solving complex robotics problems. For example, allowing us to do large-scale reinforcement learning and other type of experimentation. I'll talk about the importance of hierarchical decomposition when we devise different policies or architectures for agents and robots to carry out these tasks, and then really talk about machine learning gaps and opportunities that exist in machine learning as they relate to some of these problems. So I'm not going to belabor these points, but there's been a very large amount of progress in robotics recently. I could have probably chosen maybe 100 different videos here from Coral last year, but there's been a lot of progress in robotics, and especially as it's integrated with methods such as deep reinforcement learning. And usually these are for methods such as, or problems such as grasping, manipulation, and those types of tasks. In some cases, they might involve something like mobile manipulation and so on. And while these problems are still fundamentally hard, so there's a lot of cool works that have really tackled these problems and made a lot of progress, there's a lot of open problems as well. However, I'm actually interested in more complex tasks that allow really longer horizon complex capabilities of robots. For example, having a robot be able to move things around, clean up your apartment, bring things, again, move things from the table to the fridge and so on. And so these are very long horizon complex tasks. And I think it's sort of the state of the research community is such that we can now start tackling these, and specifically as they relate to learnable methods. And so these are tasks that are often compositional. That is, they have a lot of different sub-skills associated with them. You have to move and navigate to particular areas, pick and place, drop things, open fridges and drawers, and so on, and really interact heavily with the environment. And training of especially learning-based methods, such as deep reinforcement learning, is especially hard in these kinds of cases. It's very costly, time-consuming. These methods are often very data inefficient. And so really interested in a range of problems that we can solve in order to make headway in these fields. And so I'm going to talk about what do we need to start making progress across very long horizon complex tasks. And I'm going to argue that it starts with better simulations. So again, these are very costly and difficult things to solve in the real world. And so simulations that specifically allow continuous robotics tasks, that is not just moving from viewpoint to viewpoint, actually navigating in the environment in a continuous manner. And this involves, because the robots have to interact with the environment, deep integration of something like physics and rendering to support these kinds of things. And again, doing so in a fast manner. And by doing so, we can then support more compositional and complex tasks. So I'll talk about a range of environments and simulations that we have worked on in collaboration with other organizations like Meta, such as our RoboVLN, Vision Language Navigation environment, as well as Habitat 2.0. I'll also talk about the importance of compositionality, and specifically when we're tackling these very long horizon tasks, we really need to decompose the task into different components involving perception, but even in the space of action. For example, we might want to have high-level policies that leverage our understanding of how robotics pipelines have been developed that inform low-level policies. So this compositionality will show is actually crucial in actually solving these long horizon tasks. And then finally, I'm going to argue that there's still a lot of open questions, even in fundamental machine learning and perception communities. So for example, use of unlabeled data, self-supervised learning, tackling problems such as continual learning are still wide open problems. And specifically the integration or the movement from data sets such as those gathered on the web to real robotics types data sets really will need to push this forward. For example, a lot of these problems are studied in the machine learning community on web data sets that are kind of toyish from the perspective of robotics, because often we have a lot of other types of challenges that happen in robotics that aren't really covered by them. And I'll talk about some specific examples in my group that we've worked on that really amplifies or shows this. Okay, so I'm going to start with our RoboVLN work, which was in ICRA, and this is in collaboration with some researchers at Facebook. And specifically, we're dealing with the problem of language-guided navigation. So the problem here is you're given a natural language instruction, and of course, this is a natural interfacing mechanism to robotics, and that robot has to follow these instructions in a photorealistic environment, such as a simulation environment. So here's an example. You can say, exit the room, make a right, head straight until you reach the entrance, and so on. And so the agent has to follow these instructions without knowing explicitly what the goal is. There's been a lot of work, again, in the computer vision community looking at this, for example, using the Matterport data set. But what I'm going to argue is, again, they were studied in very, for example, discrete action spaces where you could jump from viewpoint to viewpoint. And these are not very realistic to solve robotics type problems. And so that's really what we strove to tackle, which is, can we leverage these data sets, these annotations that are already there, and really make them more roboticsy, such that we can tackle them and then eventually put them on real robots. And so here's kind of an overview. Specifically, what we did is we took the existing vision language navigation data sets, something called room to room, and really made it into a robotics problem through the Habitat simulation environment. So rather than having jumping from viewpoint to viewpoint in an environment, and for example, getting from the start to the goal in like 10 steps, how can we actually have continuous movement in the environment and obstacles and all sorts of types of things that happen in the real robotics problems? We're also not getting rid of key challenges, for example, doing this via just first-person visual observations. So we don't want to require state information or other types of SLAM mechanisms, really just given the visual stream of input, can we perform this task? And actually, because we made it more roboticsy, the stream of input is much more dense now, rather than, again, jumping from viewpoint to viewpoint over a sequence of 10 viewpoints. Can we actually do this over thousands of viewpoints as we're moving? And again, this makes it a very long horizon problem. And one of the key things that we're trying to do is decouple, again, these neural network architectures to solve these problems into various components. So for example, there's the visual and spatial reasoning that is taking the visual data and encoding them using neural networks into some feature space. Similarly, doing that for the textual part. So in the instructions, we have text and natural language. And so can we encode those, again, using neural networks? And then we want to do cross-modal grounding. That is, we want to relate the stream of visual or sensor information that we see with these instructions. And of course, this has to be done across a temporal, resolution, as well as ultimately feeding into a neural controller that actually gives low-level commands to the robot. So again, one of the key contributions that we've made is actually turning those more computer vision data sets into kind of this robotics problem. And again, one of the key things that we found is really effective at solving this as a baseline is a decomposed policy. That is, having, rather than an end-to-end reinforcement learning kind of method that learns one big neural network policy, actually decomposing it into multiple level hierarchy, which I'll talk about. And so these are kind of the overall contributions of this data set that we call RoboVLN. Specifically, we made it in continuous action space rather than jumping across discrete viewpoints. These are therefore longer horizons. So it's on average 4.5 times longer number of steps to solve these tasks. There's more visual frames. So over the entire data sets, there's up to 3 million frames. And there's a lot of environmental complexity because we're leveraging the existing vision language navigation data sets that already existed. They're heavily semantic. So the instructions reference things like television and door and things like that that have semantic meaning and show up in your visual data. And then finally, we've developed various controllers and planning methods that actually take the trajectories that were, again, sparse in annotation and actually densify them using, again, dense controls-based methods. So now we have Oracle expert trajectories that are dense that can be used to supervise models that we want to learn. So in comparison to existing methods, there's a lot of cool works that have tried to densify a little bit some of the discrete action space vision language navigation work, for example, VLNCE, which is great work. But what we find is that our environment and setting actually densifies this even further. So we have, again, trajectories that are hundreds and in some cases up to 1,000 length. So that's how many times the neural network policy has to output controls to a robotic system. As well as what's interesting is it also makes the action space a little bit more uniform. So on the left, you see the distribution over the action space. Again, this is the high-level action space, not the low-level controls sent to the robot. And what you see is on here, our RoboVLN problem actually involves a much more uniform thing. So the robot can't just learn, for example, to always say, move forward, move forward, move forward, because that's not dominated in the data set. And so this shows some visualizations of, again, our data set that we've developed, leveraging the Matterport data set and the habitat simulator, where we can actually, in a continuous manner, navigate across these spaces. We can bump into obstacles and have all sorts of different challenges that can happen when you're commanding your robots to move in continuous space. And so the one overall approach that we've developed in order to solve this, again, this is a baseline in order to kind of move the community forward, is to develop hierarchical decompositional architectures that tries to solve these vision RoboVLN tasks. And specifically, we decouple a lot of different aspects ranging from visual reasoning and imitation learning, as well as sort of the high level guidance or outputs, such as moving forward with low level commands that a robot might need to actually move. I will say, of course, hierarchical composition is not a new thing. There's obviously options framework and reinforcement learning and options critic. There's feudal neural networks, and there's even some work at UW looking at conditional driving. Our key contributions here is, first of all, showing that such compositional methods are great baselines for much longer horizon tasks, again, up to 1,000 time steps. We're using very rich semantic tasks that, and again, because we're borrowing from the vision language navigation data sets, we have rich semantics and types of objects in these environments. And these are referenced in the natural language instructions. And one of the key things that we show is important is this cross-modal method that we use state-of-the-art transformers to, for example, relate the textual instructions with the visual information. So this shows the overall architecture, and I'll go through it briefly. Specifically, in the input space, you have RGB and depth data. Each data is encoded independently using a convolutional neural network into some sets of features. And similarly, we do this for the textual information. We can use various transformer architectures or LSTMs in order to encode the textual information into embeddings or vectors. And then what we found is actually having cross-modal transformers that have cross-attention across these modalities is really important. And we think it's important because, again, grounding between what's mentioned in the natural language instructions, such as stop at the television, is really important to basically be able to align the word television with what parts of the visual information relate to that. And one of the interesting findings that we also had is that doing this independently across the modalities of RGB and depth is actually important. So you want to have cross-modal grounding between the natural language instruction and the RGB, as well as the depth information separately, because that gives you richer cross-modal grounding. And then, so that's another component. And then, of course, we have the high-level action decoder. Like I mentioned, we have a hierarchical policy here where the high-level outputs high-level actions such as move forward, take a left turn, make a right turn, go backwards, and so on. And so these sub-goals are then output by this neural network architecture and fed into the low-level architecture, which again takes some visual data and is conditioned on the sub-goal information from the high-level policy, and then outputs low-level commands to the robot. So this is a cool architecture. Again, we realize parts of this might have existed, and what we're showing is that this baseline is actually really strong in terms of solving these long horizon tasks. And so we can actually measure experimentally how well does this compare with a whole range of different types of agents, ranging from agents that use prior sequence-to-sequence neural network architectures. They might use Progress Monitor, which we developed in ICLR 2019, which is an auxiliary kind of loss function that improves performance, as well as all sorts of different auxiliary self-supervised tasks that have existed in the state of the art. And what we show is all of those are actually not necessary if we just have this hierarchical policy. Our method really improves performance when it comes to success rate, which is SR, so the percentage of time that the agent performs this navigation successfully, that is follows the instructions to the correct goal. And then there's other metrics such as SPL, which is success rate as a ratio of path lengths to make the robot not be able to take very long paths, as well as navigation error, which is how close do you get to the goal. And so through all of these metrics, again, the hierarchical method performs really well. And so we hope that this baseline, as well as some of these state-of-the-art baselines, it will really be able to be used by researchers to propel the community forward to be used for continuous tasks. And so here's an example where we show, for example, that I haven't shown the architecture for this, but a flat policy that's a neural network that just literally takes in visual inputs and outputs low-level commands without the hierarchy, has trouble performing this task. So for example, might bump into the walls more often and so on. So it kind of gets stuck here at the wall and isn't really able to move through tight spaces such as doors as successfully, whereas the hierarchical method is actually able to much more successfully perform these instructions. So we have a range of quantitative and qualitative assessment to make sure that these hierarchical methods are actually superior. Okay, so that's one task. Can we take a vision language navigation and instructions and then follow them in a simulated environment? But this doesn't solve more complex tasks, such as those involving mobile manipulation. And so there's a question of how can we both develop new methods for testing these as well as make progress. And so I'm going to present some work that we presented in NeurIPS 2021 as a spotlight paper called Habitat 2.0. This is in collaboration, of course, with Dhruv Batra and Meta and a co-advised student, Andrew Sazat. And really, again, the key motivation is that training these methods where we actually do mobile manipulation is, again, slow, expensive, error prone. The robots can fail, break themselves, and so on. And so what we want to do is do this in simulation. But once you add interaction with the environment through manipulation, where you have to have high fidelity physics, this makes the simulations really slow. And so then it's unclear how to use or develop learning-based methods, deep reinforcement learning, for example, where it's pretty data inefficient. So you might need millions or even billions of steps of the environment to actually carry these out. So this shows a video demonstrating this task. So you have essentially the robot, again, moving around in a simulated environment. The environment is super high fidelity and photorealistic. It has these articulated objects such as drawers and so on that the robot can interact with. And the key idea is, how can the robot perform these tasks that I'd like robots to do? Clean my apartment, bring me my beer, and so on. And so again, these are very long horizon tasks. The robot has to do multiple things. It has to navigate, open and close things, and so on. And so the first question is, how can we even develop a simulator that's fast enough to allow us to make scientific progress? And so we've done this in several different ways. The first contribution of this NURBS paper is something called Replica CAD. So Replica is a really super high fidelity 3D reconstruction of real world environments, such as homes. And it has lots of, again, real things in it, obviously, and is just reconstructed to a very high resolution. And so we add various, we add various things to this, such as taking the objects in that environment, having artists actually create CAD models of the objects. So obviously from a 3D reconstruction, you don't get CAD models. So we have to create CAD models. We have to add texture and other types of material properties. And then we have to make the things that are articulated, right? Such as drawers and so on. And so we had a bunch of, at Meta, a bunch of various artists actually spend a lot of effort doing this. And of course, this is released to the community so that they can take advantage of this. Once we have that, we actually want to then simulate physics for these articulated objects, such that the robot can interact with them. And through a range of different optimizations, I'm not going to go through this too much, but there's a lot of different optimizations that were made for the physics and rendering integration. So there's a very deep integration of the physics and rendering. There's localized physics, so only do physics where the robot is and is going to interact with things. There's interleaved physics and rendering so that we do things simultaneously with some latency, and then all sorts of different caching and optimization. And this has really led to 2 orders of magnitude improvements in speed that we can run this simulator in this Replica CAD environment compared to the prior existing simulation infrastructure. And this really scales not just across CPUs, but also if you use it for across 8 GPUs, the scaling is really good, such that, again, you can get orders of magnitude improvement. And this is really a key enabler of deep reinforcement learning. Without this, we just cannot perform all these large scale experiments to allow reinforcement learning agents to learn these long horizon tasks. And so this is a table showing some example comparison to existing benchmarks such as iGibson and so on. And again, one of the key highlights is really the speed with which we can do this without sacrificing the types of actual physics simulations that we do, for example, rigid and articulated dynamics. So we can do both these high fidelity kind of physics simulations at a rate that deep reinforcement learning can be studied. In order to study this, we took some simpler tasks to begin with, such as the pick task. So literally a robot is near an object and needs to pick up the object. And in reinforcement learning, what we're typically interested in is not just training performance, but generalization. So we can try to assess generalization to entirely new objects themselves, new layouts of the environment. So I didn't mention this, but in the Replica CAD environments that we developed, these have a lot of different macro variations, that is complete rearrangements of the entire kitchen, for example, as well as micro rearrangements, such as replacing similarly sized objects. And so we can test the generalization of the pick policy that's learned in reinforcement learning to these types of things, as well as different receptacles such as fridges, drawers, and so on. And so the key problem that we're solving here is what is called the rearrangement task. Given the state of a set of objects, and this could be one in the beginning, but also multiple objects strewn across the environment, we want to take that starting locations of all the objects and have a robot rearrange them, that is, move all the different objects to different goal positions. So that's the rearrangement task. And so the world is composed of, again, these interactable elements, piecewise rigid objects. We do abstract grasping. Of course, grasping is a very difficult challenge, still an open problem. So what we have is a grasping mechanism that the robot still has to determine when to grasp objects, but the end effector only has to be near the object to some degree. This is without loss of generality. We can't actually change it. There's nothing that has to be really changed except a couple of variables or configurations in the environment. So we can actually do this. It's just that we don't study it in these particular experiments. And the robot doesn't really have any access to world state. We can, of course, have it do SLAM and all sorts of other things. But as a starting point, essentially, we're doing deep reinforcement policies that take in, perceptual information and output a policy of what to do. And so over the entire paper, all of the experiments took about 6 billion steps. Again, reinforcement learning is data inefficient. Of course, there's lots of cool works that try to make them more data efficient, but it's still an open problem. And so between all the experiments, it took a lot of steps. And if we did it in other simulators, it would have taken hundreds of days, whereas in Habitat, we could do it in less than 3 days to reproduce the entire paper. And again, these are engineering contributions that are really crucial to moving scientific progress forward. The policies that we learned looks like this. This is a monolithic reinforcement learning policy that just takes in visual data, and we can, of course, explore whether we have just vision or vision and depth or a combination of them. We also have as input state information. And again, we can perform experiments to see whether we actually need state information. It turns out we can actually do pretty well without state, just using a vision only policy. State does improve performance slightly though. And then we can have these as inputs to the reinforcement learning policy. Of course, it has a recurrent neural network to integrate information across time. And then we use distributed PPO as an optimization method that has a value estimator as well as an actor network that outputs actions. And here, the actions that the robot outputs is an end effector displacement. So the end effector has to move in a particular way. And then we implement this using IK and a PD controller to actually move the joints to achieve this end effector displacement. So of course, we need to do large scale experiments in reinforcement learning. So we could do this across many domain randomizations. We add different levels of clutter, random different types of objects, and so on in order to train these policies. And again, this has been known to be a key thing that we need to do in reinforcement learning to make and learn effective policies. What's cool is that we also have implemented baselines that look at traditional non-learning based methods. So we want to understand what is the relationship between learn and non-learned methods. So this is a traditional, what we call sense plan act, decomposed engineered pipeline, where we have a task goal. We decompose that goal using sampling-based methods into particular achievable goals, places we might want to move the end effector. Again, we have a motion planner that actually plans out trajectories that can achieve the movement from the start position to the goal position. And then we have, again, a controller that actually achieves this. And so here's an example where the robot has to pick out something from the fridge. So it obviously has to move its end effector close to that particular object. So we do this by sampling many different positions around the goal, figure out ones that don't collide and that are feasible using inverse kinematics. And then we now know what place to put our end effector given our current end effector position. In order to do this, we actually use, again, trajectory-based planners like bidirectional RRTs, but the input to those are going to be sensor data. So for example, we integrate depth information across time into a point cloud, and this is the input to the RRT. And so we plan with these bidirectional RRTs given the sensor data. And then again, this is enacted once you have a plan that is a set of joint end effector positions that you want to move to. Then we again use a PD kind of controller to achieve those. And so this is the example of the engineered method looking at the sensor data and achieving and executing the plan. I will say we also have an interesting upper bound that is a privileged information sense plan act method that actually takes in the actual model from the simulator. This is one of the advantages of the simulator. We can disentangle different error things that might happen during execution. So for example, rather than accumulating information from point clouds, we actually literally give it the models that the simulator has in the environment. And so now we know with perfect model information, can the trajectory planner work? We also actually give it perfect kinematic control. That is, we actually move the joints to particular positions instead of using the PD controller. And so again, using these, we can actually disentangle different errors that might happen, so we can actually focus on different parts to perform research. So there, across all of these experiments, we have a lot of interesting findings. So first, we can test the policies on trained environments and objects. So this is on scene data. So environments and layouts that the neural network has already seen during training. And so unsurprisingly, it does really well and actually does better than these sense plan act methods. Now, I will say there's lots of new state-of-the-art sense plan act research occurring in the robotics community. So this is really just the foundation pushing forward a simulation environment such that you can explore your own favorite methods to see how well it does. But the sense plan act method doesn't perform as well as the reinforcement learning based method. And the privileged information obviously adds information and really improves performance. Now, of course, the interesting thing we want to look at is generalization. So we want to, for example, look at how well does the reinforcement learning policy generalize to unseen layouts of the environment. And here there is a concrete degradation in the reinforcement learning policy, although it still does better than the sense plan act method. Once we move to new objects, we know deep learning is not good at handling distribution shifts of the input data. And of course, this is what new objects do. And so we want to actually pick up new objects. And so, obviously, the feature representations that the neural network has learned to take the visual data and encode them to represent what the object is and where it may be, obviously are no longer really good because it's deep learning. And so you can see a noticeable degradation. And now we're actually starting to be worse than privileged information sense plan act method. And then once we go through new receptacles, that is moving, from fridge to drawers or different types of bowls and things like that, now the reinforcement learning policy is really getting much worse and compared to the sense plan act methods, which are much more robust. So this is really interesting. This, again, the fast simulation allowed us to really compare large scale reinforcement learning to traditional methods, which is always kind of something that we have intuition for example, that reinforcement learning, given large amount of data, will do really well, but it'll do well under the conditions that it has been trained on, whereas the hand engineered methods will do really well. Humans are awesome at engineering these kinds of systems, and we have a lot of cool algorithms that do well, developed over decades of robotics. However, the upper bound of these methods may not be as much, and these methods require just significant amount of engineering effort that might be hard to put in. Okay, so that was a very simple pick task, but what I argued is that, well, we want to tackle is very long horizon tasks. So we actually developed something we call the Home Assistant Benchmark, which has these kinds of tasks. And specifically, we're moving now from hundreds of time steps to thousands of time steps. This requires the use of multiple low-level skills. You have to navigate to a place, you have to pick up things, you have to open drawers, and so on. And of course, to test generalization, we often do this again on unseen layouts and configurations. And the methods that we compare are very similar to what I showed. A monolithic reinforcement learning policy, it's the same thing, except now it also moves the base rather than just moving the end effector. We have task planning that I'll talk about to actually decompose these tasks into multiple subskills. And then these subskills are either reinforcement learned or our sense plan act method, either with or without privileged information. And so these show some of the cool types of tasks. Again, something I really want my robots to do. For example, clean up my house. And this is just given a configuration of lots of objects, let's say things on the couch. Can the robot move all those objects to some goal configuration, which is a clean house? One thing to note is that this doesn't involve things like opening drawers and stuff like that. Whereas we have another task, prepare groceries. This is much more complicated. It involves the robot putting things in a fridge, which is a tight, confined space, very hard to do. And then all the way to setting the table, which involves opening drawers, taking things out, again, opening and closing the fridge, things like that. So that's really a hard task to do. And so in order to assess reinforcement learning, instead of doing an end-to-end learnable policy, which is hard to do, and again, open area for future research, which we can do now using our simulator, what we had is a task planner. So we had strips-like planning system where we used PDDL language to encode the tasks into a set of starting conditions and goal conditions. And then a planner actually determined which reinforcement learning based skill to call, as well as the inputs that that particular skill should get in terms of its goals. And so this is what an example looks like. For example, we had a set of starting predicates where you have different objects starting at different positions. Different things were closed, for example, the fridge and drawer, and we knew that some of these objects were inside these receptacles. And then the goal position or goal configuration is really where these objects are in new positions and no longer inside the fridge or the drawer. And so we can have, again, a set of actions, and these actions are reinforcement learning skills that we learned independently. So we learned a pick skill using reinforcement learning, we learned navigation, and so on. And so a planning system can just take the starting predicates and the goal predicates. And of course, this is just traditional planning methods that can actually give us at each point in time, what skill should we call and with what parameters? That is, for example, what object should we go to? When should we pick it up? Where should we take it? And so on. And so that's what the planning system method does. And so now we can actually, again, compare reinforcement learning based methods. We could compare a monolithic reinforcement learning policy that, again, does not have this strip space planning. It just learns end to end, given our sensing data, what to do. We can have our task planning plus skill-based reinforcement learning method, and then we can have task planning plus our sense plan act method, either with or without privileged information. And one of the cool things is we can actually assess how well it does, not just at the end, but also evaluate partial success. That is, because we have a planner now that actually knows how to achieve these plans, we can actually assess the task performance or success at each part in this plan. And so, you can imagine the robot has to navigate to places, pick things up, navigate to somewhere else, place it, and so on in succession. And we can compare these different methods. And so basically, here's an example of the task planner plus skill-based reinforcement learning. And what you see is the neural network, again, at each time step, the planner tells the reinforcement learning agent which skill it should be performing, and specifically what goal configuration it should achieve. And it does that, and it does these, and again, very long horizon tasks. One thing you'll notice, and this is true with pretty much everything, the performance decreases as you need to do more interactions with the environment, that is, navigate, pick things up, and place them. And this is just because of compounding error. Of course, if you have any error in the placement skill, for example, then as soon as it fails, it can't move on. And so you'll have a compounding set of effects. And this is really highlighting, again, the challenge of robotics, which we have. And so we can compare, again, not just the learnable based methods, but we can compare different methods, including the sense plan act method. What you'll see is, in this case, actually for these long horizon tasks, the sense plan act method with privileged information does the best, although it's still an open challenge to really perform these very complex tasks. Whereas the reinforcement learning agent actually does pretty well. It's in second place. But of course, again, as the length of the sequence of subtasks that we have to do increases, it just starts failing because of these compounding errors. The monolithic method here on the bottom just simply cannot learn. So this, again, just like our prior work, shows the importance of hierarchical decomposition in reinforcement learning. In this case, it's not end-to-end learned. It's a really interesting challenge to think about how we can learn it in an end-to-end manner. We can look at the grocery task, which is again a harder task. Preparing groceries, putting away things. Again, putting things in a fridge is really hard, especially when there's clutter and so on. And what you see is, again, this is an open problem. So now that we have a very fast simulation environment, we have all the baselines, including monolithic and planned reinforcement learning, as well as sense plan act. I think this will really allow researchers to take this environment, hopefully, and really move forward. How do we solve these long horizon tasks, which is a significant challenge. And as you can see, none of these methods can really solve this. So we look forward to all the cool progress that's being made over the years. So some key takeaways here are, first of all, that flat policies really struggle compared to hierarchical policies. Sense plan act pipelines that are hand engineered are brittle compared to reinforcement learning methods. Again, that's not to say that the current robotics methods that are state of the art can't be applied and through a lot of engineering be used to solve these tasks. I imagine they can be, but again, the downside is that really it takes a lot of tuning to these particular problems to develop these pipelines. So it's a very difficult thing, whereas the reinforcement learning methods are obviously more general in the sense that the same method can be applied to these more complex tasks. However, generalization to test sets that are unseen is still difficult when you have unknown objects. And the hierarchical methods in particular suffer from something we call the handoff problem. For example, one skill that navigates and to a particular position with the object doesn't get close enough to actually put it down. And because these skills were trained independently, one skill does not know what state in the state space to put the robot in such that the next skill can actually be set up for success. So this is a cool research problem, such as how to chain these skills together that we've actually started looking at. Okay, so I've really motivated this, the fact that we need a fast simulator in the form of Habitat 2.0, and we also have RoboVLN for vision language navigation to really start exploring these tasks. And we've shown a lot of baselines and a comparison specifically between modular and non-modular policies. And we showed that very commonly hierarchical policies that have high-level outputs from a neural network in terms of what subtask to do to a low-level policy actually is much more trainable. And so this is really cool to see. There's still a lot of open problems such as reward specification and things like that that I'll talk about later. One of the key things I want to motivate now is that there's actually also some really fundamental machine learning computer vision problems that my group has been looking at in order to solve these tasks. So it's not just about reinforcement learning and doing this really fast in a simulation environment such as Habitat 2.0, but also solving fundamentally some of these generalization issues that happen in deep learning. And so my group has simultaneously been also working on non-embodied tasks and really progressively moving some of these things, which in computer vision and machine learning, we look at in kind of using web data that doesn't really have the necessary problem characteristics to transfer to robotics. So this is why I'm excited to really have built a group that has half kind of machine learning, computer vision people, half robotics people, such that we can really look at the integration of these two types of things. And I'm going to show some work from our published literature from our group that really tackle these and show exactly how fundamental computer vision and machine learning problems, if solved, actually help more realistic robotics problems. And so specifically, one hint that I already gave is this lack of generalization. For example, when we had the monolithic reinforcement learning policy, when it had unseen objects, it really started to fail. And so this, again, is well known in deep learning. And so we have actually a bunch of recent work that's state of the art in the machine learning community that we've developed, for example, semi-supervised object detection called Unbiased Teacher. And we have some in submission as well that really gets state of the art results in detecting objects when you have both labeled and unlabeled data. And what we've done is try to port this into more interesting problems that is relevant for the robotics literature, such as, for example, open set object detection. So again, robots are going to see objects that they don't have in the training set. And so really dealing with these open set object problems is really important. And so we've shown that actually our semi-supervised learning methods really can solve some of these open set methods that's in submission. We also show that methods such as self-supervised learning can really also improve performance in these vision language navigation tasks, for example. One of the nice things in robotics is that it's not just a challenge, it's also opportunities. We know robots, as they move the environment, will inevitably get all sorts of unlabeled data streaming from their sensors for free. And so really the advancements made in computer vision and machine learning in self-supervised learning really is starting to be brought to bear both by our groups as well as other groups as well. Another key machine learning technique that we've developed and made headway on is out-of-distribution detection and uncertainty calibration. That is, neural networks that have probability distributions that are reflective of their uncertainty. And so this is really important in robotics. We know uncertainty is crucial in robotics. You never want to make discretized decisions. You want to really reflect on the uncertainty that the robot has to be able to plan out, for example, many possible trajectories or plans for the robot to execute. And we'll show actually in an example that this actually can feed into more realistic computer vision problems such as semi-supervised continual learning. So again, in robotics, we never want to train a model and statically deploy it on a robot. That will never work. The robot will inevitably encounter things it has not seen. And so what we want is continuous updation of the information, otherwise known as continual or lifelong learning, but with the presence of unlabeled data, and specifically out of distribution unlabeled data. So I'll specifically talk a little bit about this example to really show how this pipeline of flow from machine learning, fundamental machine learning and computer vision problems that we tackle and solve and publish on in those communities can really feed into real world robotics problems. And then of course, reinforcement learning by itself is not solved. And so there's a lot of different things. I talked about task chaining, that is chaining together multiple skills. That's something we're working on. Another key issue in reinforcement learning, of course, is hairy reward functions that you have to engineer. And so we're working on improved inverse reinforcement learning methods, and that's ongoing work. So I'm going to give a really quick example. I'm not going to go through the math because it's not really a machine learning talk here, but I just want to show you the entire progression of here's a fundamental machine learning problem. We can solve it to some degree and publish in those communities and then apply them to more realistic robotics problems. One example is that I mentioned out of distribution detection. This is a binary classification problem in machine and deep learning. Specifically, you want a binary classifier that literally just says, does a particular data come from your training data that you were trained on, or is it a different data set? So if you have two data sets, one of which was applied during training, and then another one of which that was not, can a binary classifier just distinguish examples from those. And I'll show why this is actually useful in practice. But we've developed various methods to really improve these out-of-distribution detection methods. And of course, it's related to calibration, where we want the neural network to output reasonable uncertainty estimates such that we can distinguish using a scoring function, whether it's in or out of distribution. So again, I'm not going to talk too much about this, but some baselines include, of course, just taking a deep learning model and using softmax output distribution. But those are well known to be overly confident when they see out of distribution items. There's other methods such as Odin that apply Platt or temperature scaling and various tricks, as well as density-based estimators using Mahalanobis and so on. One downside to all of these, and something that does not happen in robotics, is that this actually requires out of distribution data during training. So again, in computer vision and machine learning, sometimes assumptions are made, such as out of distribution data you can get from somewhere. Whereas in robotics, again, getting these kinds of outlier things is hard to do. We don't really want to assume that we have that available. And so we have a CVPR paper. Again, I'm not going to go through the math, where we actually explicitly model the conditional, not just of the class label given the input data X, but also a latent variable of whether something is in or out of distribution. And then we use laws of conditional probability and other derivations to actually derive this divisor dividend structure in the math. And we model our neural network architecture over that. Again, this is a CVPR paper called Generalized Odin. I'm not going to go through it, but it can achieve state-of-the-art out of distribution detection results. And again, we published this in a computer vision community and looked at the traditional data sets that are looked at, right? CIFAR, LSUN, and so on. And by the way, we have even better method that's recently in NeurIPS Spotlight paper that looks at actual disentanglement in a geometric way of a classifier into the norm and angle component and things like that to do better calibration and outer distribution detection. Again, I'm not going over this, but this is just published in the machine learning community. And so you can ask, what can you do with outer distribution detection? Is it just an academic problem that we study in machine learning and computer vision? And so one example that we have that's really concrete is something we term semi-supervised continual learning. Again, an agent moving through an environment will inevitably have to learn multiple tasks in a sequence. That is the problem of continual or lifelong learning. And it'll have to do it using also unlabeled data. And so we have a realistic kind of setup problem formulation where we have to leverage unlabeled data to learn new object categories in a sequential manner using both combinations of labeled and unlabeled data. And so the question is, how can we do this? And how do we deal with realistic distributions of data? One of the key things I want to mention is in robotics. When a robot is in a kitchen environment, for example, it'll encounter correlated streams of unlabeled and labeled data. For example, it'll see similar types of objects in a kitchen. And so there's a correlation there. And you might think that's a weird thing to think about, but actually that correlation destroys some of the methods that have been developed just in the pure computer vision and machine learning community. And so I'm not going to go through this very slowly. I'm just going to quickly talk about the method. But the key is, given unlabeled data and labeled data, we use outer distribution detection to determine what's labeled and unlabeled and drive them or pipe them into different parts of the loss function, either cross entropy losses or distillation losses, such that you don't forget old tasks, which is a key thing in continual learning. But the key point I want to highlight is not really the method itself. It's just that this fundamental problem of outer distribution detection, we can actually apply to real problems that we'll have in robotics when we perform, for example, continual learning. I'm kind of running out of time, so I'm going to fly through some of these other examples. So there's other examples. So our method does really well, needless to say, since we published it. And this is both under the setting where we have no correlations, which is the traditional machine learning computer vision setting, but also when you have correlated data, our method compared to some of the other methods that assumed things about web data and that you can no longer assume when you actually are an agent moving in an environment and gathering data are no longer effective. They completely fail, which is, again, interesting to see assumptions in machine learning communities leading to failures when applied to robotics tasks. Okay, so I'm gonna fly through this to wrap up. I do have another example that I won't cover, but self-supervised learning, that is, we have some methods in iClear that we developed called progress monitoring, like an auxiliary task of predicting how close you are to the goal that you can do for free during training, really improves vision language navigation. And also one of the nice things about, again, robotics is that you can think of many different self-supervised learning tasks that are not possible on just web data. And so this is some ongoing work that we've developed that is in submission, looking at what are the unique opportunities when you have an agent moving through an environment to develop self-supervised auxiliary losses to improve feature learning. Okay, and again, I'm not going to go through that. And so, and finally, we have another line of work that's ongoing, looking at the reward specification problem. This is work with Meta and led by Franzi, looking at inverse reinforcement learning. And again, moving from toy tasks all the way to the Habitat 2 tasks that are much more complex, and showing that our methods can really generalize to those. Okay, with that, I'm going to wrap up and take questions. In summary, I've argued that to solve these really challenging, complex, long horizon robotics tasks, we need several ingredients that my group is working on, ranging from better simulation work with Meta, Habitat 2.0, as well as RoboVLN to really study these methods in a scientific manner, developing modular, generic, generalizable neural network architectures that disentangle some of these things, which we show is crucial to solving better, more complex tasks. And then finally, really making fundamental improvements in machine learning and computer vision, and taking some of those assumptions that we make when we publish in those communities out and making them more realistic, such that they are what agents and robots encounter in the real world. Okay, so cool. With that, I'm gonna take questions. This is, needless to say, all the work of my great PhD students, collaborators at Meta, Dhruv and Franzi and others, and funded by a range of funding sources. So with that, I will take questions.
I had a quick question.
Sure.
So first, yeah, this was very cool. I hadn't realized we had so many common interests when we were talking earlier. What do you think? So for instance, like you train something on fetch. What do you think is the biggest barrier for like taking that and putting on the real robot fetch? That's like assume in the easy case, like the environment is actually what's represented in the virtual environment. Yeah, so what's gonna not work immediately? And one comment I had here was, I was, for instance, really surprised. We worked with Alfred, that like it's just been so many years in robotics that we're working on 3D sensors, but all of these methods that are being developed were just based on RGB images, assuming you don't have depth. And it was really confusing as a roboticist at first. So just noting that, but I'm curious about what do you think are some of the big.
Okay, so I guess I'll answer the two parts. So the first part is, yeah, sim to real. And I will say, I mean, that's a big interest. We haven't really done work because I think we're not there yet. One of the interesting, I think, things that can really propel the field forward is doing sim to sim. So there's lots of simulators. So can we translate these policies across simulators and then to real robots? Of course, I will say Dhruv, I think, has some existing work from Habitat 1.0, which looked at some of the simpler goal navigation policies and showed that actually you can transfer them to the real world. So I think to some degree, these things are definitely transferable. I think the perception side is definitely at this point really transferable because our simulators are so photorealistic. I think, of course, especially if you have different embodiments, that's where you'll start going wrong. So I think if you do fetch to fetch, again, I believe with small amount of fine tuning, you should be able to do pretty well. And again, you know, we're not trying to remove the need for learning at all from the real world. I expect you might want to fine tune a little bit on the real world, but the point is to move the training mostly to the simulator. So I guess to directly answer your question, I think the perception side, I think will generalize pretty well. Again, with the caveat that if it's new objects, new types of things, then the generalization will be more poor. I think the embodiment and you know the action space, if you have a change in action space or the degree of freedom and things like that, I think then that will really require a lot of research, new research to develop new methods to generalize them. But I think the good news is, you know, I think the evidence shows that if you use the same robot and the same environment, an object, then it should generalize pretty well. I guess to answer your second question, which is related to depth, again, I think a lot of, you know, these things, I have a weird history, right? I started hardcore robotics and then moved machine learning, computer vision, and now I'm moving back to robotics as well. And I think, you know, I see this progression where it is true, you know, in computer vision and machine learning, we often study things that kind of were in the beginning of robotics, right? And I think this is just the natural progression. If you notice, there is a lot of work that's starting to incorporate SLAM, depth estimation, all sorts of the things to habitat and vision language navigation and also those things. So, you know, I don't think that they're going away. I think really it's just a natural progression that if we can't solve it using just simpler information to any degree, then you know, all the things that require a lot more engineering and a lot more complexity is kind of hard to start from. We typically want to start from simpler policies that take in raw data. And of course, in deep learning, we often have this preference from end to end to have everything end to end. And that's not necessarily where we want to end up, you know, but that's where we start. And then we start incorporating, there's a lot of new works that come out that look at semantic mapping, SLAM, depth information to incorporate it. And that does help, but it is hard to make it help, I will say. And part of that is because it's a larger engineering effort. Yeah.
Thank you. So, yeah, you mentioned the fine tuning. I think it will be also interesting for that to be systematic, right? Versus.
Yeah, absolutely. And I think that's a big research question. How do you fine tune and especially drive down the amount of actual real world experiences you need? And also I think this idea of disentangling, so disentangling perception from high level policies, which maybe are more generalizable, and then maybe having only parts of the neural network model fine tuned. I think there's a lot of interesting research questions there for sure.
Thank you, Zol.
Yep.
With that, thank you very much for presenting We really like to talk, and have a great day.
Awesome, cool. Thanks for the opportunity. And I enjoyed it. And if anyone's interested, check out the publications and feel free to reach out to me.